Good morning, students. I'll start with the class. In the previous class, we were doing topic surface tension. So surface tension is nothing but, suppose if you have any substance, okay, and there are some molecules in it. So whenever it comes across contact in surface, this is the surface. So along this surface, there are some forces which act upon the molecules. These forces are called as forces of attraction. What is going to happen is the molecules try to attract either towards this surface, okay, or this surface. So this is also a surface only with reference to the molecules. So they try to attain minimum area. Okay, they try to come closer as much as a smallest area possible. They try to attain. So what they're going to do is they can either form like this. So what has happened? They have tried coming closer. So they have ran away from this surface. So that's why you feel like this type of surface tension. That is one possibility. The other one is like this. Here what is going to happen? All the molecules will go and stick towards this surface. Here area will become empty little bit. Okay, so these molecules will go and stick here. So two ways a surface tension can lead to, and that area what is called as meniscus. I told you. The shape is used. And we don't use the word shape. We use the word meniscus. So for kerosene, you will have something like this, and for mercury, you will have a meniscus like this. So you know this is a convex one, and this is a concave one. Over here, what is going to happen is this. What is this is going and sticking this surface. So this particular area, just see the shaded area, okay? This will become wet, and this particular area, you see, here the water molecules or the mercury molecules have ran away, okay? The liquid molecules have ran away from the surface, so this is going to be bit dry. Here the fluid is coming and sticking to this surface, so this will be partly, okay, this surface will become wet, but over here the fluid molecules have ran away, so this will be left dry. So this is the solid, this is the liquid. So here liquid will wet the solid. Here liquid will not wet the solid. And now this angle of contact, means this angle which it forms, no, this meniscus is forming some angle. See. So that angle is called as angle of contact. On page number 5 of your notes, you will have that. That is angle of contact. I'll just share the slide. Sorry. Angle of contact is the angle between the tangent to the liquid surface at the point of contact and the solid surface, which is the inside the liquid. It's a tangent drawn towards it. So for this one, this is the curve. Tangent means what? You have to take any one point and draw perpendicular towards that direction, like this. So this curve is going this side. So with reference to the surface, this will be theta. Over here, which side is the curve going? This side. This is called as a tangent. The angle of contact is theta here. So for kerosene, this is acute angle. So whenever the liquid will wet the solid, that angle is acute. Whenever the liquid will not wet the solid, means this part is dry, that time you will have a obtuse angle. Means more than 90 degrees. If you see, obviously with reference to this line, that is an obtuse angle. Here, which forces are there? Here, these are cohesive forces. They will attract among themselves, and this will be more of adhesive forces. Adhesive means going and sticking around to something else. They will go and stick to the other material. Cohesive means forces among its own molecules. So they are attracted among themselves. Here, these molecules are attracted to the other substance. That's why they are going and sticking to this surface. This was about angle of contact. Now, capillary tube. Capillary tube, you must have, well, have gone in the physics lab. It's a small, like a tube, small, very tiny, like a needle. Okay, it is having a small hole. If you put it inside a liquid, either the liquid will rise, okay, inside the capillary tube, or it will fall. The tube, the rise and the fall, whatever happens, that process inside a capillary tube is called as capillarity. If you put a blotting paper inside a water or ink, what is going to happen? That blotting paper will absorb that color. You must have noticed that blotting paper will become blue if you put it in the blue ink. So what is happening? All the small like holes of that blotting paper absorbs that water or the ink inside it. So there's an experiment done based on that. You see for the this capillary rise. We'll find what is the surface tension for that. So this is we are assuming a capillary tube. It is placed in the water or any liquid. It is all filled up. So it will the capillary tube has a property that the liquid will either rise up or fall. So now this is for a capillary rise we are looking at. This is a case where water will rise or the liquid will rise. If you can put kerosene in this, it will form this kind of meniscus. Various liquid will form various types. Now what will be the angle of contact? Consider this is your angle of contact. I'm drawing only on one side, same way it is on the other side also. Now what is going to happen? This is what the force acting on this. So it's like the surface tension across this line. Now there's always an equal and opposite reaction which is equal to this tension. R is equal to sigma. This sigma, this you can this is for tension. Huh? Now don't get confused with this. R is nothing but the reaction. Theta is nothing but the angle of contact. Now whenever the force is not 90 degree, we can always resolve it into two components. We have studied that. Anytime this is angle, we can always split this vector into two parts. The horizontal component and the vertical component. Vertical is always given sine theta and horizontal is always given cos theta. So same way, this also will split it into two parts. So with reference to this one, this arrow. So with reference to this arrow, you can just twist this and see. This is R, no? So this is your horizontal one for this. For this arrow, what is the horizontal one? This will be like a x-axis and this will be like a y-axis for this particular graph. I'm just twisting this. Suppose if I draw like this, just 90 degree if you rotate, this will be the horizontal, this will be the vertical with reference to this R. So this will be sigma cos theta and this will be sigma sin theta or rho you can use. So resolve R into two components. Now this is with reference to one small point I have shown you. Now suppose if you look from top, okay, from the top view, how is this going to look like? It's going to look like a circle only. The meniscus is going to look like this in the capillary tube, whether it has gone inside the depression or whatever it may be, like how a trampoline looks like from the top view. Okay, like a trampoline, it will look like as though it is gone inside. When you stand on the trampoline, there's a depression caused. So from top view, anyways, you will see it like this only, like a full circle. So it's like the whole way all these forces are acting. This is only with reference to one molecule we are considered. So that way, everywhere there will be all this cos theta along the whole circle. Now the full circumference is how much? This is at one point. So total will be whole circle. This distance is 2 pi r. And this is your opposite weight of the liquid acting. This side will be the weight of the liquid. This side opposite is rho cos theta, and this side it is weight of the liquid. That is mg, mass into gravity. So only this is important for you to derive the formula or the surface tension. So we know that what is the weight of the liquid is always m into gravity, mass into gravity. You know that density or surface tension is mass upon volume. So mass will be always, so instead of m, I will use as rho into v into g. If you want, you can write this at the side and keep mass upon volume. See the difference, huh? This is for density. They look similar. This is for tension. This is for density. Volume is nothing but area, this total area into the height. So rho is always area into the height. Length, breadth into height. This is not this, what is that? This is not rectangular where I can use length, breadth and height. This is circular. So this circular is how much? Area for the circle. This is the circumference. Area of a circle will be pi r square, because this is circle we are considered. Outer distance is 2 pi r, but inside the area is pi r square. Next part. Now this is 1. Weight of the liquid is this. So you can mark it as equation 1 and keep. Next is the vertical component. Now as per the reference line, this is the vertical component from our point of view. So that was how much? This sigma cos theta. Force acting per unit length. You know the definition of surface tension. It is nothing but the force acting per unit length. So what will be the force acting? Now what is the overall force in the vertical direction? That will be cos theta. Keep it as F first. Instead of this, now the resolved component, the vertical one we are looking at. So this will be sigma cos theta. Length is how much? 2 pi r. Why we got this? Because only we are taking the vertical component. Now if you see this force, this is the force which is acting upwards. At equilibrium, both these forces, equal and opposite forces, should be equal, no? At equilibrium, no? At equilibrium, weight, this weight, mg, is always equals to the force, opposite force. So weight of the liquid is given as, and this is given as, so equate both of them. Equation 1 and you can say equation 2. So equate equation 1 and 2. Now whatever is getting cancelled, you can cancel. Pi and pi will cancel. 1 r will cancel. So we are finding the surface tension. So it is rho r hg upon 2 cos theta you bring down. So this is the answer. This is the surface tension calculated for a rise in the capillary tube. It still solves the problem. Before solving the problem, these are the formulae. We know that surface tension is nothing but force per unit length. Then work done. Last time we had seen this two types of drop. One was liquid drop and the other one was soap bubble. For soap bubble, we have to use 2 times surface area. For soap bubble. Why? Because it is hollow inside. So whenever we are taking the surface area, we have to take the inner one also, outer one also, 2 times. Within work done is always surface tension into increase in the area. I'll write it properly. Work done is surface tension. Anytime you ask to calculate work done, you have to use this formula into increase in surface area. W is equal to change in the surface area or the surface area. This is the work done. Also used as the word energy. Even if you are asked to calculate energy, you have to use the same. They also say call it as increase in surface energy. Energy, work, same formula you have to use. In case you have to find pressure for liquid drop, then it is we are derived also this, and for this is double, is 4 times, because we have to use 2 times this, two surfaces. The pressure for hollow is 4 times the surface tension on its radius. Let's start with the first problem. Calculate the work done in blowing a soap bubble from radius of 2 centimeter to 3 centimeter. The surface tension of the soap bubble is 30 dyne per centimeter. So the radius is increasing from mu r to 3 centimeter. This is the first question. Calculate the work done. And what else has been given? Surface tension has been given. That is given as 30 dyne per centimeter. We are solving problems from page number 6. Now everything is given in terms of centimeter. So first one, no need to convert. If one was Newton per meter and this was centimeter, we have to convert this into meter. As of now, everything, all the units are in terms of centimeters. So right now we can keep it the same. No need to change. Calculate the work done. Now work done, we have seen the formula, nothing but surface tension into change in the surface area. So now this is like a soap bubble. So we have to calculate the surface area of the soap bubble. So what is the surface area of a sphere? The surface area I can consider is 4 pi r square. This is the formula. So you can calculate, substitute for the first one. Initial surface area I can consider. Now substitute. Well, taking one, you can take this also, 2 times. Why? For soap bubble, I told you, two we have to take the surface area. One inner and outer. If you want, you can write and keep inner and outer. Both. Directly we'll take 2 times. So for soap bubble, whenever you want to calculate surface area, take it 2 times. So initial, what was the radius? So 2 4 is 8. pi is 3.14 and r square. First one water, radius is taken as 2. Then final surface area after the bubble has increased into 3 square. Now we want to find what is the change in the surface area. ds is s2 minus s1. This is s1 and this is s2. This is 9. This is 4. So take this out common. 8 into 3.14 into 9 minus 4 will be common. Now calculate 3.14 into 5. What I've done, I've calculated the initial area with radius 2, calculated the final area with radius 3. Now I have to see how much the surface area has changed. S2 minus S1. We will get around 125.6 centimeter square. You can calculate this first also, no problem. Calculate this value, and this minus this. Now work done is what? This is the formula. Surface tension is already given as 30. In the question it is given as 30. And this ds we have calculated just now, 125.6. Now work done is, we are doing what? CGS system. Why CGS? This was given in terms of centimeter. Everything we have taken in terms of centimeter, if you see. In case you want to convert it into SI system, if we had converted this into meters and all, then work done would be 3768 into 10 raised to minus 7 joules. If you want to convert it into joules, no, this is SI system. Ergs can be converted into joules by just multiplying it with 10 raised to minus 7. Work, unit of work in terms of CGS is ergs. And this is joules. Even if it started with this centimeter into meters and all conversions, and then yes, you would have got the same answer. But why to take a headache of first converting everything into meters? Everything was in CGS only, so we have calculated and just last multiply it by 10 raised to minus 7 and get the SI unit. You can keep the answer like this also, no problem. Second question. The surface tension of a soap solution is 0.03 Newton per meter. Now this everything is there in terms of meters. How much work is done to produce a soap bubble of radius 0.05 meter? Surface tension is given as 0.03 Newton per meter, and radius is given as 0.05 meter. Now, if this was given in meter and this was in centimeter, we have to convert it into meter. Now, both are in terms of meters, so no need to do anything. Now, it's a soap bubble. Surface area will be, you have to take 2 times, I told you. Now, work done. This is what, maybe this is a fire, this, uh, now there is no this, it starts from 0 because we are just making the soap bubble now. So even if you do the final and the initial also, it's like starting from 0 to this. So no other change is there. The radius anyway is not changing. So directly you can use the formula into ds. Now directly this is your ds. Why? Because there is no other this. If from R1 it was going to R2, because anyways when the soap bubble did not exist, we consider radius as 0. So anything you calculate, the surface area before was 0. So even if you minus the other one, S2 minus S1, so it would be whatever is this minus 0. So directly you can substitute now because there is nothing else to calculate. This is 0.03 and ds is this 8 into 3.14. You can, if you don't, you can use like this also. 5 into 10 raised to minus 2 the whole square. 5 square is 25 into 10 raised to minus 4. Then calculate and then write your answer. Work done, whatever answer you get will be in terms of joules. Third one, a liquid drop of diameter d breaks up into, okay, so there's a liquid drop which breaks up into like this 27 drops. This is one drop. So it is breaking up into 27 drops. Find the resulting change in the energy. Take surface tension of the liquid as this only. The surface tension anyways is this symbol, one drop, and this is 27 tiny drops. So then nothing else given, so how to go about it? If you notice this volume, this big volume, no, volume means how much matter has been used to form the space. Even if it breaks, what is going to happen? So if you combine all this, all the 27 tiny drops, all the volume if you add, it should be equal to this because they all formed from this much volume. Volume of the bigger drop is equals to 27 into volume of tiny drop. Because if all this, if you multiply by one volume, this will be this volume into 27. If you multiply, it should be equal to this. Now this once the diameter is given as d. Volume of big drop is how much? 4 pi r cube is 27 times. We'll consider this as r and this fellow as capital R. This r they have given directly in terms of d. The diameter is given as d. So what I'll use? Radius is nothing but diameter upon 2. Open up the bracket. Now r cube upon d cube. This is 4 to the 8. Okay. I've taken it properly now, yeah. And now we'll take a cube root on both the sides. This volume of the drop, correct now? Tiny drop. Why the 2 is coming up, I'm just seeing that now. D cube, suppose it will be 2 into 27 r cube. If you take a cube root, turn out to be 6. I'll just check out. Cube by mistake, it's 4 pi r square. You're considering the surface area, not the volume. Sorry, 4, I took this, what is it? It's a 4 by 3 pi r square. Just correct the formula. Just correct this. And I was thinking what went wrong. They've done some mistake there, beta. They're using, or actually volume formula is pi r cube. I don't know why they're using pi r square. everything, that solution only is wrong. Better confirm this because yeah, it's 4 by 3 pi r cube, 27 times. Just add 4 by 3 only. I was correct actually. Only 3 I had missed out. Anyway, that would also cancel. This 4 also would cancel. The smaller one you use. The solution which they have given there's some mistake. This is correct. Then pi and pi will also cancel. Okay, so capital R cube is equals to 27 times smaller r. Now r cube is what? Cube root of 27 r cube. Okay, because they have used the formula there 4 upon 3 pi r square, which is wrong. Volume of a sphere is always 4 upon 3 pi r cube. So this will be 3 r. Cube root of 27 is 3 cube root now. R cube. So r will be cube root of this. So 3r will be your answer. Now d is how much? R can be taken as d by 2, which is 3r. So d will be 6 times r. Okay. So capital R is 3 times the smaller r. So r means how much? Total distance upon 2. The total diameter upon 2. So this is the relation. D is 6 times r. Now we'll find out what is the change in the surface area. Initial surface area must be how much? Initial surface area will be 4 pi r square. That is of the big drop. Final surface area will be of 27 drops. Now this is the surface area formula. So this will be 27 into 4 pi r square. So what is the change in the surface area? We can do S1 minus S2 also, no problem, because distance anyways cannot go negative. So we usually take either whichever turns out positive, higher minus the smaller you can do that way. That will be 27 into 4 pi r square minus your 4 pi r square. Okay. If you want, you can substitute that in terms of this, the relation. R is 3 times R. 3 times smaller r. So 27 into 4 pi r square minus 12 pi r, and work done will be nothing but is a square, no? Wait a one second. So this will be 4 pi into 9 r square. So 27 into 4 pi r square minus 36 pi r square. So multiply this and then minus from here. And work done will be nothing but your, just add row to it. Whatever answer you get here, this will be 4 sevens are 28, 108 pi r square minus 36 pi r square. So just minus this. So whatever answer you get, you write. My answer is in terms of r square, smaller r square I've given. If you want, you can convert it back in terms of d then, and then write the relation. So work done will be, just minus it from here. So row into 76, sorry, 72 pi r square. So this will be the answer in terms of radius. If one can convert in terms of d also, r you can take by d upon this 6. We want to convert it back up. This is 72 into pi into d square upon 36. This is 2. So 2 pi sigma d. This was in terms of small r. This is in terms of capital R, capital D. In case you want the answer in terms of capital D, because in the this what is it, the question solution they have given this way in terms of D. So you might not get, should not get confused. What did I do here? Why this 72 came? I just converted it back in terms of D, suppose. Now the fourth one is exactly same as the second one. Fourth is same, you have to solve as second one. Fifth is same as the first one. Sixth is again same as the third one. Instead of 27 drops, you have to take 1000 droplets and calculate. Again, seventh one is also same. Just try this problem. They're same concept. It is. You can solve and then send it to me. I'll check if you have solved it correctly or not. Just refer whatever was second, third, exactly same way you have to solve. Only thing now in the problems they have given the diameter, so you can just substitute the diameter there or the radius. The next ones which are there, no numericals on surface tension that needs that capillary tube, that barometer and all, which I'll be doing at the end of the chapter. So those problems also I will solve. Numericals on surface tension. Once I do that topic of the barometer and all, I'll solve this problem. The next topic is laws of flotation. It states that the body floats in a liquid when the weight of the fluid displaced by it is equal to the that of the body. Means what is, suppose if you put anything in the water, whether it should sink, okay, or whether it should float depends on the weight of the body. There's a weight of the body acting downwards, and there's something called as a buoyant force from the liquid which is acting upwards. The weight of the body must be downwards. So while drawing like this, and opposite is this called as the buoyant force. Now it's obviously understood, if this weight is very weak, if this fellow is not able to push it up, this will sink. The first one, this is going to sink completely. Then W is going to be greater than your buoyant force. Weight of the liquid, the weight of the object is more than your buoyant force. This W is weight of the object, the weight of the body. Second one, when it is equal, so it is going to be above the yeah, it's going to float. In the third case, when the this will be partly one, okay. There the diagram, there's something they've not given. When the buoyant force no is more than the weight, it's going to float completely. Or you can say if its weight is this, partly you can say, not exactly float, like partly submerged. Why? Because the weight of this is going to throw the water little bit out. So slightly it will be inside. Yeah. What is going to happen? It is less than this. Is there given in the notes? They have not numbered them. So this is first one. This is the second one, and this is the third one, partly submerged. There are no much questions asked on that. Next one, Bernoulli's theorem. Now this is important. Applications normally, the derivations, I don't think so. They ask. In case it is done in your college, then let me know. Because derivation, only the statement and the applications are important. Suppose if you have a tube, and there's a water which is entering and then going out. Okay. Now if you see, there will be some area. Let this area be A1, this area be A2 of the tube. Obviously, from the diagram, it's understood area A1 is bigger than A2. Let P1 be the velocity of which the water is entering with, because obviously water is entering or the liquid is entering with some speed, and this tube is kept above some height. With reference to the main line they are referring, so you can, this is H1, this will be H2 from the center of the tube. Okay. With some speed, what liquid is entering, so there will be some kind of force. Okay. You know that pressure is nothing but force upon area. So what will be force? Pressure into area. So based on the area, there will be some pressure. So this side we'll name it as F1. Same way, this side we will name it as F2. There will be some force. So the three things which you need to know is the area, A1. So V is nothing but velocity of fluid. P is the pressure of the fluid, and A is the area of cross section of tube. Cross section means this, from this point of view. Now, what Bernoulli tries to say that no matter how big this might be, okay, if you see this area is bigger than this one, although it is small, what is going to happen? The pressure and the volume will always change accordingly. If there is a this what is that high speed now, pressure will be less. Yeah, if there is a lower speed of fluid, then the pressure will be more. So based on that, this will try to adjust among themselves in such a way that the total energy, whatever is there at the starting, will always be at the end. Now, just because this tube is big, we cannot say here energy is more and here energy is less. Accordingly, the volume and the pressure will change. If velocity is more, pressure will always be less. If pressure is less, this. So it tries to keep this should remain always constant, P into V. So if this increases, this fellow decreases. If this one decreases, this one will increase. And make sure this number will remain same. So Bernoulli tries to say that the total energy of any incompressible and non-viscous fluid in a streamline flow. Then what is that streamline flow? We will see in detail later. So basically, the energy at the starting, the energy at the end is always equal. This is what it tries to say. So which are the total energies involved there? What is that incompressible word? Incompressible means cannot be pressed. You cannot change the volume of the fluid just by putting pressure. No, you cannot reduce the water or reduce the liquid. Cannot be pressed or reduced. And non-viscous. Viscous means what? Like thick. This. If you compare water and honey, okay. If you pour water in a glass, it will fall fast. It's non-viscous. But honey, if you're trying to pour, it will take some time. Okay, it's little bit thick. So that is called as viscous. It should not be viscous in nature. It should be non-viscous, normal flow. So with total energy, Bernoulli says that total energy all remains constant. So which will be all the energies at the start. Total energy, the pressure, kinetic energy, and potential energy is always constant. Total means all the energy. And I will not use. This should remain constant. So at the start, I'll just use the letter 1, means the number 1. So this is a this is a pressure, this is a kinetic energy, and this is a potential energy. Whatever is there at the start will be there at the end of the tube. So this is Bernoulli's statement. Total energy at the start of throughout the tube will always remain constant. So how does it remain constant? So whenever velocity increases, this is very important. When velocity increases, pressure decreases. When velocity decreases, pressure increases. Now, based on this, we will see the applications of Bernoulli's theorem. Only this you need to know, this much for the applications which I'm going to explain next. So remember, whenever velocity is high, pressure is low. Whenever pressure is high, velocity will be low. First application, second. I think uh, this is missing that. Here. The applications. So what does the Bernoulli's theorem say? The total energy of the fluid per unit volume. So wherever you consider at the start, maybe any given any volume, total energy always remains constant. So application is first one is the sprayer or a atomizer. Means you want to spray out some liquid. So there's a diagram given. This is so just draw that and explain. Just a rough one. Okay, so this is the rubber ball, and this may be the nozzle. Now what happens is, before the rubber ball is been pressed, nothing. Everywhere the pressure is constant. There is air in this. There is some liquid in this. Okay. Now you are not doing anything. It is at equilibrium. So what is going to happen? Normal it is. So everywhere pressure, volume, everything. Not, there is no change in anything. So whatever is the pressure here will be the pressure here. Now what you going to do is, when you press the rubber ball, the air will start moving this side with a faster speed. So what is going to happen? Velocity, whenever this is pressed, velocity of air increases. Velocity of air increases means pressure decreases. So what is going to happen? Here velocity is high, pressure is low. Throughout this, velocity of the air is high and pressure is low. Now what is going to happen here? If you compare, right, before pressing the ball, everywhere volume, velocity and pressure was same. At the moment now, comparatively, what has happened? Volume, velocity went high of the air, so pressure went low. So if you try to compare this P1 and here maybe P2, so pressure obviously decreased means this fellow is smaller than this. So here what is going to happen? Pressure is going to increase to maintain the same thing. As per Bernoulli's theorem, everything has to be maintained. So pressure increases means in this box, so this pressure is going to means start pushing this liquid upwards. This high pressure will try to put this liquid upwards. It will mix up with the air, means the speed of the air. So what is going to happen? The speed of the air is going to take the liquid droplets also along with it and going to spray out. So whenever we press the rubber balloon, the air rushes out in the horizontal tube, decreasing the pressure to P2. Okay, here they have used the word P, which is less than the atmospheric pressure P1. Here they have used P1. This was the atmospheric pressure. Compare it to outside also. Now what is going to happen? As a result, this liquid will rise up and then This is the vertical tube. In this A it will come and then mix up with this air and it will be sprayed out. So basically what you have to do is once you press the ball, the velocity of the air increases. Over here pressure will decrease, which is comparatively smaller than the outside pressure, and here if you compare, this pressure will be higher. So this pressure will push the liquid up and then it's going to mix up with the air and be thrown out. The second one, the burner is there. So there's a in the gas, what happens is there's a gas which is being supplied through a fine nozzle with a high velocity. So whatever gas is been there, it is coming with a very high speed. So obviously what is going to happen, there'll be a low pressure. So there'll be a low pressure here, high velocity of the gas. Over here I'm talking about the gas is coming with high velocity, so the pressure will be low. Now what is going to happen? Here comparatively pressure is going to be high. So that because of this high pressure, it will start coming inside. Air will start coming inside. And whenever you want anything to burn, you need air. So what is going to happen? This spark, whatever is happening, this air will push it up and it comes in terms of flame. So that gas, who is giving it force like this atmospheric pressure will start coming in this air, will help this gas to come out of the burner in terms of flame. So this gas velocity is high, pressure is low comparatively, outside pressure is more, so it will start coming in and then it will come out in terms of flame. So only this concept you have to remember whenever there's high velocity, low pressure. Third one, so during cyclones and all, if you see some of the roofs and all will get blown away. House roof. Why does it happen is because the outside wind, what is blowing, is high velocity. During cyclone, the wind is blowing at a very high speed. So what will happen? This will create low pressure. Now if you compare it with this one, what is going to happen? This will be low at lower velocity compared to this. So since this is at lower velocity, this will be at higher pressure. So now this high pressure will start acting upward. And because of this pressure, this roof will be blown away. If this is not like joined properly, this pressure is enough, strong enough to create this, and the roof will blow away. The main thing, the outside cyclonic winds are having high velocity, low pressure. Inside, what is going to happen compared to this? This will have whatever air is there inside your house will have a lower velocity compared to this. So it is going to create a higher pressure. So this pressure will start acting upward and try to remove the roof out. Fourth one is the aerofoil. Aerofoil means the wing of the this, what is that, aeroplane. So what they do is they design the aerofoil in such a way that, I'm just trying it roughly. What there'll be air, they've shown it the other way around, okay, whichever side it may be. Now there is wind which is blowing upwards also and downwards also. But this aerofoil is designed in such a way that whatever wind is coming, no, means air is blowing above this will always flow at high velocity. This curve is designed in such a way that the air which is blowing upwards will be at higher velocity. This air is at lower velocity. This side it will take some time to flow. The speed is slow. Here, speed of the wind is fast. So what is going to happen here? Low pressure will be there. Here, high pressure will be there. So what is going to happen? This high pressure will start pushing the wing up. So that is the how it helps the plane to fly upwards, not downwards. Imagine if this ulta was done. Here wind was blowing fast, so there would be high pressure here. And this side, high speed means there would be low pressure, and this pressure would put the aeroplane down. But it is made ulta. So high velocity here, so lower pressure. Here, lower velocity, so high pressure. This high pressure will make the wing fly upwards, push upwards. Fifth one, it is dangerous to stand near the edge of the platform when the train is moving fast. So there's a train, there's a person standing. So what is going to happen? The air which is moving along with the train over here is moving with a very high velocity. So what is going to happen? This will be at low pressure. Now compared to this air, now the person where he's standing, this air will be at what? Low velocity to compare with this, because this is moving very fast. This air is moving with the train. So this is at low velocity. So there will be high pressure. Now this high pressure will try to push the person towards the train. So because of the low velocity, there's a high pressure created, and because of the pressure, the person might be pulled, pushed towards the train. Okay, so that's why it's not suggested to stand close to the train when it is moving very fast. Let's stop here. The remaining also same logic you apply. High velocity, low pressure. Okay, the other place it will be always high velocity, lower pressure, or the ulta way, low velocity, high pressure, and then it will be pushed towards. So Bernoulli's theorem says that whenever pressure is high or velocity is high, pressure will be low, so that it keeps the total energy constant. Next class I'll start with the streamline and the turbulent flow. Stop here. If you have finished, you can leave.